So we have talked about lots of different kinds of forces. We've talked about tension forces. We've talked about normal forces, gravitational forces. It's time to talk about friction forces. And a lot of the problems we've done so far, we've said, well, this is on a frictionless surface. But that's woefully incomplete if we're going to characterize our actual universe. We got to deal with friction because, well, surfaces have friction. So let's just run a little experiment here. I have on my desk this ridiculous calculator, right? They don't make them anymore, which is why I bought it. It was cheap and discontinued. It's basically an 89 with a QWERTY keyboard. You can launch the shuttle, I think. I'm not sure why it's on, but there you have it. So it's got these little rubber feet on the bottom, so that if you try to push it, it doesn't move very much. And so what I'm going to do is I'm going to actually do that. I'm going to push on the calculator. Move it up here, and you're going to have to take my word for it that I'm actually pushing, right? I'm not pushing very hard, but I am pushing. In other words, I'm applying a force to this calculator. Now, what's the calculator doing? Absolutely nothing. It's not doing anything. It's not accelerating. So I'm applying a force. You maybe even see my finger, right? Let's zoom in a little bit. You can see my finger getting a little white there. I am actually pushing on the calculator, and it's not accelerating. It's doing nothing. So let's first of all come back in. Let's do something of a free body diagram here. Now, we'll look at the calculator from the side. We'll say that it's sitting on the table and I'm looking at it from the side. And so here's my calculator. And we'll say that this is my applied force. Now, we know that the calculator is not accelerating. So if I write Newton's second law, what that means, if it's not accelerating, that means the right-hand side is 0. Which means the left-hand side is 0. But as I've drawn this, that's impossible. I know that I'm applying a force. But if I only have one force, it's impossible to balance that. You can be in equilibrium with 0 forces. You can be in equilibrium with 2 forces, or 3 forces, or 87,000 forces. You cannot be in equilibrium if you only have one force acting on you, if it's non-zero. So what this is telling us is there has to be another force. Furthermore, it has to be opposing this one, right? It's got to be equal and opposite, not an action-reaction pair. The punchline here is, why is it not an action-reaction pair? Because it's acting on the same object. The punchline here is this is the force of what we call static friction. I'm going to subscript that with an S, force of static friction. What does static mean? Static means sitting still. Dynamic means moving, or really it means changing. Static is going to mean not changing or sitting still. And so there's a certain type of friction here. I push on the calculator and it pushes back, right? But it's a certain kind of friction called static friction. Now, again, you're probably going to have to take my word for this, but I promise I'm being honest. I'm pushing a little bit, and I'm getting very little force back. How do I know that? Well, I know that these forces have to be equal and opposite. So if I push a little bit, what that means is that I'm getting a little bit of force from friction. But I can increase the amount of force that I apply. And I'm actually, you can see my fingers getting white. I'm pushing relatively decently here. Well, what that means is that the friction force is getting bigger also. Maybe that second time, my system looked like this. It means my friction force, my static friction force, is doing this. I can keep that going, right? Press a little bit harder, a little bit more. Finally, I start to move the calculator. At some point, the static friction lets go. Does that mean there's no friction? No. But it does mean that there is a different kind of friction. We'll talk about that in a second. First, I want to look at this. We see that there is a maximum value that the static friction can have. 2 things to notice. Number 1, it responds to my applied force. Number 2, it has a maximum value. After that, there is no more static friction. I've gone into kinetic friction. So I'm a physicist. We're going to graph things. So this is going to be the force of friction. In this case, it'll be static, but we're also going to put the other kind on here, so I'll just leave it as F sub F. And here is my applied force. All right, fair enough. So if I don't apply any force, I don't get any force back. There's no static friction force. So 0, 0 has to be a point in this. But after that, we saw that if I applied a little bit of force, I got a little bit of friction force back. And that continued. As I got greater and greater, the friction force got greater and greater. Turns out that's a linear relationship. And it looks like this, where this is the maximum value. This is the maximum value of static friction. Put that on the wrong axis, right? Okay, fair enough. After that, after I reach my maximum value of static friction and this thing starts moving, like I said, I no longer have static friction, I have kinetic friction. But interestingly, that turns out not to depend upon the applied force. It turns out to just be a thing. We're going to talk about what it depends on, of course, but it turns out to just be a constant frictional force. As long as I have the same object, this thing, on the same surface, the kinetic friction force now, right? The friction of motion, the kinetic friction force turns out to be a constant. Really interestingly enough, it turns out to be here. So here's my static friction. Here's my static friction max. That is my kinetic friction. So notice there are points in this graph where the static friction is less than the kinetic friction, but the kinetic friction is less than the maximum value of the static friction. Now, I will submit that you probably know this already instinctively. If we were pushing a heavy couch across our living room, I don't know, I just moved a couple months ago, so this is in my mind. I keep using heavy couches as examples. But if I'm pushing a heavy couch across the living room, most of you would, hopefully all of you would agree with the statement. It's easier to keep it moving than it is to get it started, right? Here's why. As you're pushing on it, you have to overcome this maximum static friction. Once you do that, the friction, the opposing force you're getting is here. It's less than the effort you basically have to put in less effort to keep it moving than you did to start it moving, because the kinetic friction is always less than the static friction. All right. How do I characterize these mathematically? As it turns out, these are material specific. In other words, and that's something you also know, right? But you all, maybe, at least you've seen it, have gone or seen ice skating. Nobody ever skates on sand, right? That's a bad plan. We skate on ice because the friction on ice is very low. Skating on sand won't work out well. So it turns out that the amount of friction that an object experiences turns out to be a function of the surface over which it's moving. So we characterize those surfaces by things called coefficients of friction. The symbol for that is the Greek mu. It's a Greek m. It looks kind of like a u, but it's not. It's a Greek mu. And we subscript the mu with a K for kinetic friction or an S for static friction. So this is something you could look up on a chart if you were doing an industrial application and you need a relatively low friction surface, say like Teflon. You would look up this material list, find out what has the lowest coefficient of friction in your price range, and use that material. Static friction, same thing, but we're going to have to talk about this a little bit more to see how we would use that. Normally in industrial applications, I imagine you'll be looking more for kinetic friction, but they're both related. And each material will have a coefficient of static friction and a coefficient of kinetic friction. The coefficient of kinetic friction works like this. If I'm looking for the force of kinetic friction, that will be equal to mu k times the normal force being exerted on the object. I hope that makes some sense. if the coefficient of friction arises from the particular surface that you're on, and the normal force is just a support force from that surface, maybe it's obvious that there should be a relationship there. So mu k times the normal force gets you the kinetic friction, always. And this is an equivalence. Remember our graph. It's just a constant. No matter how much force I put on this thing, I apply to it, I just get this constant frictional force back. Mu k is a constant. The normal force, as long as I'm not piling on mass, is going to be a constant. So I get a constant frictional force. This, however, is not constant. So I have to deal with that with an inequality. The force of static friction is less than or equal to mu static times the normal force. Less than or equal to, well, when is it equal to? You can probably imagine, or you can see mathematically, the maximum value of the static frictional force occurs when it's equal to mu static normal. These are both positive quantities. So when is the static friction equal to mu static normal? That's right here, the max value. Over here, it's less than that. But that's the max value. So if you're going to use this in a problem, make sure it's a problem which is asking you something like it's just about to slip, or it's on the verge of slipping, or the static friction force is maximized. They usually don't say it so plainly, but all of those mean the same thing. This graph also gives you a clue. If this is equal to mu static normal when the frictional force is maximized, and it's equal to mu kinetic normal when it's moving, well, mu kinetic normal is here. This is mu k normal. This point is mu static normal. You can see from the graph then, for any given material, mu static is greater than mu kinetic. You can't have a mu static of 0.6, say, and a mu kinetic of 0.8. That doesn't work. The mu static will always be bigger than mu kinetic. Okay, this is a coefficient. It is dimensionless. You can probably see that from here. I've got newtons here and newtons here, which means this can't add any dimensions to it. So it's a dimensionless quantity. Its size will be directly related to the friction force you get. The larger the mu kinetic, the larger the kinetic friction force. Larger the mu static, the larger the maximum value of the static friction force. A couple other things to say about friction. Most importantly, direction. These are vectors. They've got to have direction. Friction forces always oppose either motion, in the case of kinetic friction, sorry, let me get that where you can see it, or impending motion in the case of static. Always, always, always. Go back to my calculator. If I'm pushing on it, the direction of the force I'm applying is that way. So the impending acceleration, therefore the impending motion, since this is at rest, is that way. So as I'm pushing on it, that means if the impending motion is that way, the static friction is acting backwards to that. Once it starts moving, the motion is that way, which means the friction force is opposite of that. It always opposes the motion or the impending motion. That's got to make some sense if you just remember your brakes in your car. Nobody ever hits their brakes and then speeds up. If you do, you didn't hit your brakes. You hit the other one. The brakes cause friction between your brake pads and your discs, most likely if you have disc brakes, which pretty much all of you should. It causes friction, which opposes their motion, which is what slows you down. So it always opposes the motion.